All right, hello everybody. Today we are going to be talking about the metric system and a little bit of scientific notation. So let's just dive right into that metric system. In chemistry, we will only be using metric units, or we might also call them SI units, which is after the French term for international system. These units were adopted by France, and we have used them ever since in the sciences. Now, the question is, why do we use the metric system in science instead of the United States customary units? And the answer is because most other countries use the metric system. So all of those SI units and standards and metric units are universally accepted and understood by scientists throughout the world. It would be very confusing when communicating about science between different countries if we didn't have the same understanding for what a measurement meant. So to keep good communication, we use one system of measurement across science, and that is the metric system, or the SI units, the International System of Measurement. So let's dive into what that looks like. Every type of SI measurement has an associated unit. These are the 5 main types of measurement that we are going to be using in this class. Length is measured in meters, the lowercase m there. Mass is measured in kilograms. That's the SI unit, or the standard unit, kilograms, which is a capital K-G. Volume is in liters. Don't ask me why the US uses liters, but we don't use meters or grams or anything like that. It doesn't really make a lot of sense to me. We should all use the metric system. I will fight with Mr. Rodaway about this later on. Don't worry. So volume, we do measure in liters, capital L. Temperature is something called Kelvin, which you may have heard of in your physics in the earth class. What you're going to be most familiar with is degrees Fahrenheit and even degrees Celsius to an extent, but we'll talk about why we use Kelvin specifically in the sciences. Time just has one unit, it's seconds. Of course, time is absolutely made up. If you think about it, we were the ones who decided that time existed. What existed before time? Great question. Doesn't matter. What you need to know is that the unit for time is seconds. That's the SI unit. Let's dive in a little bit deeper. Length. Hopefully you know what length is. It is the measurement of the distance between 2 ends of an object. So one end to the other end. The metric unit for length is the meter, although we are going to frequently use centimeters because that size is more reasonable for when we measure things in class. We won't often be measuring things that are a meter or longer, but we are going to use centimeters a lot when we measure in class. Length is measured with rulers, meter sticks, tape measures, etc. Anything that has. Moving on to mass. Mass is a measurement of how much matter is present in an object. So matter is the amount of stuff, I say that in quotes. So matter is the amount of atoms, particles, etc. that are in an object. So if something takes up space or it is made of particles, it has mass. And that is different from weight. The term weight is related to mass, but the two words do not mean the same thing. Weight, as you may have learned in physics, is more related to the gravitational force on your body, on any particular object. So if we go to the moon, we will weigh different, but we will have the same mass unless we lost a toe on the way there or something. The official SI unit of mass is the kilogram, although we will usually use the unit gram in chemistry because that's the metric base unit. That's the metric standard, but it's not the SI standard. So SI is like the next level of scientific everything. So the kilogram is the SI unit, but we are usually going to use grams. And we will measure mass with a balance. Volume. Hopefully you know what volume is. It's the measurement of how much space something takes up. So there are a couple different ways we can do this. The metric unit or SI unit of volume is liters, although again, milliliters is frequently used because that size makes more sense for the things that we will measure. But You can also measure volume in cubic centimeters. You would use cubic centimeters to describe a regularly shaped solid object. For example, a cube, or think about a dice. It has all those sides, so length times width times height. You would measure each side in centimeters, multiply them all together, and you would get your volume. We will use milliliters when we are measuring liquids. We might also measure some solids with milliliters, but we will get into that at a later date. So because you can determine volume in a couple of different ways, we can measure it using a variety of equipment. So this water displacement is what I'm talking about. We can determine the shape of, or the volume of irregularly shaped objects by water displacement. And we will put that in action in a little bit. Temperature. So this is the fun one. Maybe you remember some of these terms from physics. You'll understand that I'm saying that a lot because A, to remind you that you just took physics last year, and B, chemistry and physics are very closely related. So temperature is a measurement of the average kinetic energy of the particles in a substance. Kinetic energy, if you remember, is the energy of motion. So if particles are moving, they have kinetic energy. The faster they are moving, the greater their kinetic energy and the higher the temperature. Unfortunately, degrees Fahrenheit and degrees Celsius aren't directly proportional to the energy of particles. And that doesn't work in chemistry. In chemistry, we really care about the particle level. We care about atoms, right? So we needed a temperature scale that would be based directly on the energy of particles in motion. And that's where Kelvin comes into play. The SI unit for temperature is Kelvin. Unfortunately, Kelvin thermometers don't exist in this sphere here, in this classroom. So we are going to measure in degrees Celsius and then convert to Kelvin. Degrees Celsius is the metric unit, right? The SI unit is Kelvin. We will not use degrees Fahrenheit at all. That system of temperature measurement makes absolutely zero sense. Google it. It doesn't make sense. So we are going to measure in Celsius and then convert to Kelvin. Of course, your next question is, how do you convert from Celsius to Kelvin? Very easy. You take your degrees Celsius, you add 273, boom, there's your temperature. Fairly straightforward, I hope. Temperature measured with thermometers. Again, that one seems like a little bit of a gimme. Let's talk more in depth about the metric system. You've probably seen this before. These are the most common metric prefixes. So you'll see kilo. You've probably heard kilograms before, or maybe megabytes, gigabytes in terms of data and stuff on your phone. Centimeters, milliliters. You've heard all of these prefixes before, just maybe not in the context of measurement. So these base units here, that would be your grams, your liters, your meters. And then by changing the prefix, we can change the size of the number that we are dealing with. So if we have 1 meter, that would be down here, 1 meter is the same as 100 centimeters. There are a lot of centimeters in 1 meter. Or there are 1,000 meters in 1 kilometer. Right? Kilometer is a large unit. There are a lot of meters in 1 kilometer. So this section here in the middle that's outlined in this blue color, these are the areas that we are really going to focus when we talk about metric measurements in class and when we talk about metric conversions. You will definitely hear me refer to micro, nano, and even mega and giga. But we are going to focus on these 7 steps or levels of the metric system. If you think about these as levels or steps, it will make converting between units that much easier. So let's dive into that a little bit. How do we convert between metric units? There are a number of ways to do this. I'm going to teach you all of them, but the most common would be to jump from level to level or move your decimal. Now, you might have seen this before, but let me show you a little bit what I mean. If we go down the table, if we do jumps down the table, that's the same thing as moving the decimal to the right in a number. So if we start with 1 meter and we want to convert that to centimeters, we would go 2 hops, 2 jumps down the table, which moves the decimal to the right. So if we have it here, we would go boom, boom, and now we have 100 centimeters in a meter. If we go up the table, that moves the decimal to the left. Now we are going to have a smaller number than we did originally because our unit is larger. So let's put some actual numbers to it. If we convert 1 meter to millimeters, we are going to make, so meters to millimeters, meters is here, millimeters is down here. We are going to make 1, 2, 3 jumps. We are going to take that 1, move our decimal, pretend there's a decimal there, we're going to move it 3 times to the right. And now we get 1,000. If we go the other direction, that would be from 1 meter to kilometers. So if we look at that, meters is here, kilometers is up here. So we are making 1, 2, 3 jumps. So we're going to move the decimal 3 times to the left. So 1, 2, 3. Fill in those zeros there, and we get 0.001 kilometers. Now this makes sense, okay? If you are maybe a runner or if you've ever been on a track, you might have heard of a 5K race. So a 5-kilometer race is 3.1 miles. That's what a 5K is. You also know how long a meter is because you've seen a meter stick before. Of course, it makes sense that 1 meter is a very small number of kilometers. Just think about how many meter sticks you would have to lay end to end to get to 1 mile, much less 3.1 miles. Moving on. Let's try to convert a couple of these. We'll do the first one together. Let's try a couple of these. I'm going to do the first one with you and then see if you can do the other ones. So if I have 0.0397 centimeters, I want to convert that to meters. So what I'm going to do is, let's picture that metric system that we are working on memorizing in our heads. Meters is here, decimeters is here, centimeters is here. I'm going from centimeters to meters. So that's 1, 2 jumps up the table. Since I'm going up the table, I'm going to move my decimal to the left. So I'm going to move this 1, 2 times, fill in that 0. So my answer is 0.000397 meters. Let's see you try. Go ahead and pause the video and try to do these next 2 on your own. So hold on, let me just erase this for you so that you can see it. It just says that we moved up the table 2 steps, right, which we already talked about. So we moved up the table 2 steps, so that's how we ended up with 0.00397 meters. Now, going from kilograms to decagrams, it's kilograms, hectograms, and then decagrams. So we are going down the table 1, 2 jumps. When we go down the table, we move the decimal to the right. So we're going to move it 1, 2 times to the right. We are going to end up with 1941.2 decagrams. That's one. If you haven't tried it yet, please go ahead and do so. This one we are making a lot of jumps. We are going kilo is up here, then hecto, then deca, then the base, then deci, centi, and milli. We are going from the bottom, from milli, all the way up to kilos. That's 1, 2, 3, 4, 5, 6 jumps. So we need to move our decimal 6 times. Which direction? Since we were going up the table, we need to move to the left. So we are going to take that 398. We're pretending that the decimal is here. We are going to move it 6 times to the left. 1, 2, 3, 4, 5, 6. And fill this in with a bunch of zeros. And that should be your answer, 0.000398 kiloliters. So there is a assignment on Hatchroom called metric measurement conversions. I think or something like that. So go ahead and try those practice problems, and the is provided for you as well. You can always check your work if you need to. Now let's talk about something a little bit different. We're going to switch gears slightly. We're going to start talking about scientific notation. In science, we use scientific notation to make really big or really small numbers more manageable. What I mean by that is that it's really annoying to write 3 billion out with all of these zeros. It is a lot easier to just write it as 3 times 10 to the 9th. This is the scientific notation right here. You've probably seen this before. It works both ways. We can make really big numbers more manageable, right? Just one digit, really. And we can make really small numbers more manageable, right? Very similar. You'll notice that we had a huge number over here and we had a positive exponent. Whereas over here we had a really small number, we had a negative exponent. We are going to talk about that. There are many parts to scientific notation. Let's break it down. We have coefficient. The coefficient is the first number. The coefficient is the first number in the scientific notation section. So that's the 3 in both of these. That's the coefficient. This is always a single digit number. It can have a decimal, so we could say 3.0 times 10 to the 9th, but we could not write 3 0 times 10 to the 9th. That doesn't work. This is good. This is bad over here. Bad. You have to have one digit before the decimal in scientific notation. Then we have the exponent. The exponent, obviously, is this part here. That's the exponent. It tells you how big or small the number is. If we take math and we learn, which we have learned about exponents there, positive exponents are numbers that are greater than 1. So this 3 billion is clearly a very large number, much larger than 1. So we have a positive exponent. Negative exponents are numbers less than 1. So we have this very, very small number over here because we have this negative exponent. Let's do some examples to see it in action. Take 2,540, for example. If I want to put this into scientific notation, I'm going to imagine that I have a decimal here. Then I'm going to take that decimal and move it so that there is only one digit before the decimal. So I'm going to move it 1, 2, 3 times. I want it to sit right between that 2 and the 5. Since I moved it 3 times, my number is going to end up being 2.540. That's my coefficient times 10. And then the exponent here tells me how many times I moved the decimal. I moved the decimal 1, 2, 3 times. And my number is greater than 1, it is a positive 3. So I moved my decimal 1, 2, 3 times. My number is greater than 1, so it's a positive. Oh, look at that. I have the answer written right there. All right, in the second problem, again, we have a number that is greater than 1. So we know that we should end up with a positive exponent. Our coefficient is going to have just one number, one digit before the decimal. So this is where I want the decimal to be. I'm going to move it from the right side. 1, 2, 3, 4, 5, 6 times. I have moved the decimal 6 times to the left, and I have a positive exponent. So my number is 5.649000 times 10 to the 6th. The 6th tells me I moved my decimal 6 times, and my number is greater than 1 because it's positive. Another one. So I have a number that is smaller than 1, so my exponent should be negative. And I'm going to move that decimal 1, 2, 3, 4 times. So I will get 4.1 times the negative 4 because I moved the decimal 4 times. Negative because the number is smaller than 1. Hopefully you are catching on. Here I have a really small number. Again, I'm going to have a negative exponent because I have this small number. The question is, what will that exponent be? 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Remember, I'm only allowed to have one digit before the decimal, so I had to move my decimal 9 times. That's where that 9 comes into play. 2.71 times 10 to the negative 9th is my answer there. We can also go the other direction. We can take stuff that's in scientific notation and get it out by moving the decimal and putting it either to the left or to the right to make the number bigger or smaller. So if you see in example 5 here, this is a positive exponent, which means I need to get a number that is greater than 0. In order to get a number greater than 0, I'm going to have to move the decimal between the 2's here to the right. So if I have 2.25, I need to make a number that is greater than 1. So I'm going to move the decimal 5 times to the right. 1, 2, 3, 4, 5. And then fill that in with zeros. So my answer is 225,000. Going the other way, now I have a negative exponent, so I need to end up with a number that is smaller than 1. So I'm going to take that 4.81, that coefficient, I'm going to move the decimal twice to the left. 1, 2, and my decimal is here. Fill that in with a 0, and my answer is 0.0481. Remember that you can go back and rewatch those example problems if you're not quite catching on yet, but I do want to see you guys try to complete these 4 problems. So go ahead and pause the video on a piece of paper. Hopefully you've been taking notes, so on your piece of paper, write down these 4 problems, and we're just going to do some practice with it, okay? Try to put these either into scientific notation or take them out of scientific notation. Welcome back. Here are your answers. So in the first problem, to put it into scientific notation, I know that I'm going to end up with a positive exponent because the number is greater than 1. And then you just do decimal 1, 2, 3 times. So that's where you get times 10 to the third. The second problem, my number is smaller than 1. That's why I have a negative exponent. Specifically, I moved that decimal 1, 2, 3 times, which is how I ended up with the negative 3. In 3 here, I took that 8.202 And I needed to make it a large number because the exponent is positive. So I moved the decimal 1, 2, 3, 4, 5, 6, 7 times. Fill that in with a bunch of zeros, and you get this number over here. On the very last one, I need to make a number that is smaller than 1 because of the negative exponent. So I'm going to move the decimal 4 times to the left. 1, 2, 3, 4. Put your decimal down there. Fill that in with some zeros, and again, you end up with this number over here. So I hope that you were moderately successful with this scientific notation and conversions. At this point, you should be able to complete the metric measurement conversion worksheet, and you can start the scientific notation worksheet. In order to complete the scientific notation worksheet, you will need to watch the following scientific notation math videos. So there's one more video lecture that you need to watch before you can complete both of those assignments. So if you are a virtual kid, you're just completing these assignments, you're submitting in your work like normal, and then you're going to come to office hours if you still have questions. My hybrid kiddos, you're going to see me in person next week. So you can ask questions in person. You can also come to office hours and ask questions there. I'm also 100% of the time available by email. I respond to my email very quickly, so just shoot me a quick email and I'll give you a response back.